Thank you. Good morning. Ready to rock and roll here. So first, my name is Alfred Essa. I'm Director of Innovation and Analytics Strategy at Desire to Learn. And this is my colleague, Hanan Ayad. She's a Senior Research Scientist and Technical Product Manager for Analytics. We're going to talk about design. So this is really a session on design. And what we're trying to do is put together an application and harmonize three elements of design. One is sort of product design. Second is engineering design. That's underneath the hood in the application, but we're not going to talk about that today. And the third one is research design. I will spend a little bit of time providing context in terms of product design. What's the application? So we're building an application called the Student Success System. So what's its function? And then I will assert some design principles. And there's a problem set that we're trying to solve, and that's connected to the research and visualization aspect of this presentation. We'll do a very, very quick lightning demo of the visualizations to give you a flavor of the application. And then Hanan will concentrate on the research problem set that we're trying to solve as part of the application design, and then our solution. The heroes in this story are two people, Sir Francis Bacon and Aristotle. So that's, as we go through this, think about that. Okay, so design principle number one, just going to assert that from a user experience point of view, our objective here is less data, not more data, but less data, more insights. And then underneath the hood, from a systems perspective and engineering, we need more data and less complexity. So from a design perspective on the user experience, we want less data, more insights. The goal of the application is, and the pioneer in this space is John Campbell in the Signals Project. We want to make predictions, identify at-risk students, but also a very, very important category is to identify exceptional students and then design interventions and communication for that. The workflow of the application, imagine the patient-physician relationship. So the workflow, typical workflow in that relationship is first you want to understand the problem. Next, interrogate the data. Consult with others, prescribe a course of treatment, or design an intervention, and then track the success. So that's basically the overview of the app. Design principle number two is the goal here is not prediction. It's really optimization, and I want to just explain that very, very quickly. So this is a slide that kind of goes over analytics maturity levels, kind of a shorthand for different levels of analytics maturity. So at level one analytics, it's really data about the present, data about the past. It's reporting, and at best, this is what's happening now and what happened in the past. A lot of analytics is really at that level. But analytics level two is what will happen if we don't change our assumptions or if we change some assumptions. And that's when we start to get into things like predictive modeling, forecasting. But the holy grail of analytics is optimization. It's really what we want the desired future to be, what should happen. And just one way to think about optimization is whenever you're in a current state and you have a desired future, there are multiple pathways, and the goal is to find the optimal path. So the way we think about analytics is really it's an optimization problem, finding among the alternative pathways that exist, which one is the optimal path. Okay, so now let me state the problem set in the application. The signals model, which many of you are familiar with, makes a prediction. The context is a student in a course, and it makes a prediction red, yellow, green. The limitation of the signals-like type model, and I'm going to put that in quotes because it's not to isolate signals. Signals may have gone beyond this, so I'm just going to say signals-type model. The limitations are interpretability, interactivity, and portability, and let me explain that very, very quickly. So this is a very rough conceptualization of the signals type model. We have a student and a course as input. There's a function or a model, and you get an output green, yellow, red. Now imagine if you're in the healthcare sort of example, you're a physician, and a patient walks in, and the system, the analytics says red, yellow, green. There's not much to go on. I mean, that's helpful, but if the end goal is to design an intervention, I need something more. So the first limitation of the signals type approach is interpretability. There's not enough information. If the telos, the end goal, is taking action, there's not enough information for the intervention. Second is lack of interactivity. We need to be able to interrogate the data, make sense of the data, because our ultimate goal, if you're going to design a meaningful intervention, it's about the particular case, the particular individual, and all the surrounding factors. The third limitation of the signals type model is lack of portability. Same model applied for every course at every institution doesn't take into account the variability of learning design, instructor, course context, large courses, courses in sciences, humanities, etc. So this is the basic problem set that we're going after from a research perspective, and Hanan will elaborate more on that. And also part of the answer is visualization. So let me do a quick lightning demo of the app, and we're not going to go through the entire app, but show you some of the key ideas in the app and the visualizations. So this is a student success system. Imagine you're an advisor or an instructor. You have a number of students, red, yellow, green, risk predictor, name, picture of a student. So first I'm just going to click on, I just want to see which students are at risk. One of them is Eric Cooper. I'll click on him. And this is Eric Cooper's profile chart. This is intended to provide an overview. There's some demographic data, et cetera. We see that Eric Cooper is a full-time music student, et cetera. The first visualization is a win-loss chart on the left. So we first isolated the fact that Eric Cooper is in trouble. He's at risk. And with the win-loss chart, what we are able to do is get a quick reading on what risk factors are contributing to the prediction. So we see here that his attendance rate is negative. He's not essentially logging in. His completion rate is also negative. His participation rate's kind of average, et cetera. So this is intended to give a quick glance at to what risk factors or risk domains are contributing to the prediction. Another visualization that we have is a risk quadrant. Each point, so now we're looking at the math class that Eric is a participant in. The risk quadrant is 4 quadrants. Each point represents a student in the class. Top right-hand quadrant are the students who are on track, not at risk. Bottom right-hand quadrant, we see 3 students who are at academic performance risk. That means that our prediction is that they will end up getting a D or an F. Eric Cooper, along with 2 other students, are in withdrawal dropout risk category, and then we have 2 students who are in the top left-hand quadrant, and they're under-engaged. That means that from an academic performance point of view, they'll be okay, but they're not engaged fully. At this point, a very, very critical part of the design, we need to be able to merge quantitative data and qualitative data. So I just clicked on notes, and this pulls up sort of a case history, CRM type capability. What's the case history of Eric Cooper? And I'm not going to read all the stuff in there, but this kind of gives a running account of the types of touch points and interactions that Eric Cooper has had. And we see, for example, that he's seen his advisor a couple of times, had some interactions. So this allows me to develop a better qualitative picture of what's happening with Eric Cooper. Now, if at this point I'm ready to make a referral or design an intervention, what this screen would pull up is what are all the service options that are available at your institution, and which ones are relevant for Eric Cooper. I'm going to show just one other use case. Another use case is we have Kate Johnson. And what we see with Kate Johnson is she's taking 4 classes this term, biology, chemistry, computer science, history. We have predictions associated with each one. In 3 of our courses, our predictions are green, which is going to be very successful, history, troubled waters, turbulence. So we have a red prediction. I'm going to click on Kate Johnson. We, again, look at our win-loss chart. And when we look at our win-loss chart, her attendance is okay. She's coming to class. She's completing her work. Her participation rate is about average, a little bit below average. What's troublesome is social learning. And so what does that mean? So we're going to click on sociogram, and now this is a prototype, but this is sort of the network graph of her interactions. And what this is picking up is Kate Johnson is an isolated learner. And so imagine a model or a context in a class where collaboration, group work is essential for success, and there are early signs that she's not interacting with her peers and others who are important in the context of that class. So here's some of the visualizations, and Hanan will kind of dig deeper into the model underlying this. So I'm going to turn it over to Hanan to describe the underlying modeling.
So I would like to talk about the ensemble modeling, which is the technique we're applying here to tie up and inform the product design from the scientific perspective. And I'd like to talk about 3 different aspects with regard to ensemble modeling. Again, the technique that we're applying. So the first is what it means from a conceptual perspective, what is ensemble modeling. The second point I'd like to talk about is from a statistics and machine learning perspective, why we're using that. And the third is the application domain. From an education perspective, how do we apply this paradigm, this new technique in the education, specifically for predicting student success? So in terms of what it means from a conceptual perspective, ensemble modeling really means collective intelligence. Is for us to be able to improve decision making, to optimize decision making, and Al talked earlier about optimization. We can't rely on a single expertise. We need to bring together multiple. We need to form a committee and bring multiple experts together to optimize our decision making. You can think, for example, a patient who has a problem might want to seek a second opinion, for example. Even a medical doctor might want to investigate different sources of information and bring different tests to optimize his own decision making. So the idea behind ensemble modeling is the collective intelligence and bringing together multiple expert systems to make better decisions. So if we think again of, in the context of the signals model, you have the student and the context in which the student is learning. And then you want to form an intelligent system that allows you to determine their success level, whether the student is successful, is potentially at risk, or at risk. And the key idea here is that we want to preserve interpretability, interactivity, and the accuracy of the prediction. The ensemble, from a statistics and machine learning perspective, the idea of ensemble modeling, the key motivation behind it is improving the accuracy and the generalization of predictive models. So there is actually a very large and strong body of research behind the idea of ensemble modeling. And as I mentioned, the key motivation here is improving the generalization and the predictive accuracy of these models. So instead of relying on only one model or a single hypothesis or an expert predictive model that is trained to make better decision, why don't we build multiple hypotheses? And through a process of consensus, we can combine these decisions from multiple different perspectives and optimize our decision-making process. So that's the fundamental idea here. And there are, as I mentioned, there is a strong body of research from mathematical proofs to large-scale experimental studies and benchmarks that shows how ensemble techniques can improve the decision-making process. Also, the ensemble modeling paradigm opens up a lot of design choices. If you can think about it, well, what are the different hypotheses we want to test? What are the different data sets we might want to look at? What are the different features of these data sets that each model might want to look at? And also, what are the consensus functions that can combine all these decision making? So it opens up a lot of design possibilities. And what we want to do is to leverage these design possibilities in the education paradigm, in the application in education, or in that particular problem of predicting student success. So taking that back to the design of the student success system, we want to look at the overall prediction and decompose that into multiple domains that we can build predictive models that specialize in these domains. And you can think of the social learning, for example. We can look at the social network and perform some social network analysis and even some text mining on the conversations that are going on, that's going on between students to build specialized models in the social learning space that can provide us with some predictions that are pertinent to these to this type of features and domain data sets. You can look at other things, participation or content comprehension, for example. We don't want to look at what are the number of topics that students have read. There is a difference between, for example, the introductory material versus the more advanced material and how much time they spent. Maybe they spent too much time on advanced material but not on the fundamentals. So all these domains, and then around that, there are so many other dimensions, such as the time, the different courses, the different programs, and the different competencies that the student is acquiring over time. So the idea here is to build these semantically meaningful units that we can combine their decisions in meaningful ways and tie them up to interpretive displays of the data and have better accuracy in our models. Thank you.
Just to wrap up, and this is where Sir Francis Bacon and Aristotle come in. The signals type approach, the basic limitation is that the predictions are black boxes. And what we're trying to do here is to open up the black box through this semantic units so that we can probe. So Sir Francis Bacon is the originator of the scientific method. And so we want to be able to peek inside the black box and interrogate it. And where Aristotle comes into the picture is the idea of judgment. Machine intelligence predictions are not enough. We have to couple that with qualitative data and the ability to make judgments, whether it's an advisor, the student himself or herself, as well, and an advisor. So thank you.
Thank you. So as usual, the microphone is here for questions.
Those were really nice visualizations. I liked being able to kind of drill down. One of the things that we're constantly having problems with is uncertainty. We tell our faculty, okay, use our LMS, and they say, okay, but they don't use it for class discussions because they want to use something else, or they use some new tool that we've never heard of. How does that factor into these? How can we build models that quantify this uncertainty, or at least recognize it and then ignore it? So for example, we might have a small class where discussion isn't important at all, yet we've got all these giant red bars for people that say, oh my God, you haven't been talking enough. Could you just touch on how that might work?
Yes, actually going back to the design of the predictive models, decomposing it into multiple domains that are visible to the instructor, the social learning, for example, as opposed to the participation or the attendance and so on, opens the possibility of tuning these models as well So providing them with visibility into how much they weigh in the context in which the course is taking place, and giving them the ability to have control over these weights as well. For example, if most of the discussions are actually taking place in class, face-to-face, then they might not really be interested in what's going on in the discussion forum, and they can choose to turn off this domain completely, which is contributing to the prediction. But again, it's combining multiple models. You can remove and add models as you wish. And this is the design framework that we are trying to build, is to make it modular so that you can add and remove things depending on the context in which it's used.
Thank you.
Yes, I have a similar question. To what extent are there plans to build analytics capabilities with tools that are built with the LTI protocol? So, bringing in outside tools that have this LTI data infrastructure, making it possible to add that to your models. So, like, for example, Panopto or Piazza, some of these newer tools that are built to interface with learning management systems from the outside.
Yeah, so we didn't talk about the engineering of this particular product, the student success system. So a client might say, hey, we're going to build our own predictive model, and in fact, it's proprietary, and we don't even want Desire Learn to have access to it. So it's being architected in such a way that the predictive models or whatever is generating the prediction could be exposed, and we would just pick that up as a web service. So the actual engineering of the application is intended to be flexible.
Yeah, so we have no time for more questions, so there will be some more discussions at lunch.
Thank you.